Quality of the presentation can be sent to trash. So this is total 180 from talk number 1. Let's get into some data. Right, here's the science. Also, Chris Sanders is now at Grand Junction. We used to work together at Topeka, did a lot of this work together there. So he is an equal or greater participant in this than I am. All right, so some things we're going to talk about. Let's hope I lose my voice, that'd be cool. We better start in with some definitions. All right, box and whisker charts, quick definition. I think we've seen several of them already. So we're going to see plenty more in this presentation. A couple of new terms that I want to point out. We're going to be looking at things like warm layer energy, or the max temperature of the warm layer. Get into winter mode, I know it hurts. If you thought you were unpopular with snow, boy, wait until an ice storm shows up. You also have cold layer energy, which is characterized by this blue shaded area, and the cold layer min temperature, or wet bulb temperature. We'll talk about both of them. So keep an eye on this, digest this, hold on to that for a second, and we're going to be hitting on a lot of those terms. A couple other definitions. For those who haven't heard me blabber on about ice before, you have something called the ice to liquid ratio. It's the same concept as a snow liquid ratio. It's saying if it rains an inch, how much ice will you get? A snow liquid ratio of 0.5 to 1 means if it rains an inch, you're going to get a half an inch of ice. That is the way it sets up, and that's actually the way it works quite a bit. Next one, the Freezing Rain Accumulation Model is FRAM. If you haven't used it, get excited, maybe your day will come. It is now embedded in BuffKit. I think they're throwing it in the href, so some really cool stuff. It's getting out there for people to use. The FRAM has performed well, I'll show it at the end, but there are some biases, and that's what we're trying to correct here. Maybe some situational entities that we can improve for our forecasting going forward. A proximity forecast sounding. You've heard it all in severe weather for the most part, but we're actually going to look at RAP soundings for freezing rain. Again, I'm sorry. 0 hour forecast sounding coincident in time and space with freezing rain observation. And more or less representative of the environmental characteristics at that time. We're going with hundreds of these. I could not quality control every one. We tried to use at least an automated process to get rid of the bad ones. And of course, vanilla ice, wrapper, unrelated to freezing rain, shows up constantly. I don't know why. I don't get it. Show my age sooner or later. I'm going to talk about the FRAM a little bit more. These are some important points if you have or have not used it. It is statistically based. I had to redo stats to figure out how to do the FRAM and build it. It predicts the ice-liquid ratio. It doesn't predict icing amounts. It is based on predictions of precipitation rate, surface wet bulb temperature, and surface wind speed. And let me say, garbage in, garbage out. And so we got to remember that in everything we do. This is a statistical model based on predictions. This is several layers of inception of potential failure. But it works well on observations, so that's good. Also, and this is an important one that I think that gets lost, but it is intended primarily in predicting freezing rain. It was only developed on rainfall rates greater than 200ths per hour. So whether or not that's rain, it's more than sprinkles. We got that. It has application for drizzle, but it's not baseline to that. Tips for a great FRAM forecast, and this is for everybody in here. Number 1, nail that precip rate forecast with hourly resolution if possible. This model was developed based on hourly observations. Our QPF is often 6 hourly predictions. Sometimes it's more than that. If you break that up and just divide it by 6, that's not how nature works. So that's not how freezing rain is going to accumulate either. The greatest feedback I get is that FRAM is over-predicting ice, when in reality we are almost always under-predicting precipitation rate. So keep that in mind as we're going forward. There are going to be some improvements in the forecast builder for those of you who use it, going to actually incorporate an element of hourly precipitation rate, which should improve this, but only in the near term. So food for thought, keep it in mind. And also beware drizzle, especially with strong wind. You can get some of the craziest ice-liquid ratios. Some of that is due to measurement of liquid. It's just not good, but I've seen some pretty impressive stuff. As far as the new data, just a quick overview. Some requirements for the proximity soundings. Sounding surface temperature had to be within 1 degree Celsius of the actual observed surface temperature for that observation. The forecast sounding must have a warm layer aloft for melting. There are probably scenarios where maybe you get freezing rain without that warm layer. That is a different process. We're not trying to predict that. The forecast sounding location has to be exactly the same as the freezing rain observation ASOS, and has to be within a 60-minute window of the freezing rain observation. So again, these are fairly restrictive, and then we do some quality control over the top of it, and you know, there are limitations with this data set. I know you all think the RAP is perfect, but you know, it has its limitations. I'm sorry. Some of the more common ones here, the temperature profiles during precipitation, especially convection, they get wonky. They're kind of weird sometimes, so they can't always be trusted. Sharp vertical gradients in T and dew point. You know, we see that a lot in a freezing rain. You get this crazy warm nose, and then if you go 100 feet down, you're freezing cold. So very sharp gradients, the model vertical resolution can't handle that very well. And then the vertical temperature and dew point profiles at the onset of precipitation. How many times does a model perfectly nail down onset of precipitation in a previously dry atmosphere? Almost never. So these are some of the errors that are coming into this data set. The good news is there are 447 soundings that satisfied our criteria. So that's a pretty solid number when it comes down to it. It's still only about a third of the actual icing observations we had. They are across the entire CONUS, all hours of the day. Basically, it's a good cross-section of the ice measurement data set. All right, so let's get into the deep stuff. Roll up your sleeves. It's going to get crazy. Let's do graphs. Why not? And again, I don't know if these satisfy the color requirements. It's hard for me. Here we're just looking at the warm layer characteristics. So this is, for all 447 soundings, the maximum warm layer characteristics for these events. And you're going to notice right off the bat, there's some that are less than 1 degree Celsius in the warm layer. That is almost never actually going to produce freezing rain, but there are scenarios where it will. So again, I'm just going to say up front, these are limitations of the data set. Can we trust all those? I don't know. And that's why we haven't incorporated this into the actual FRAM yet. We need to dig deeper. Temperature is in blue, wet bulb temperature in red, and they're overlapped. So one really interesting thing, you got a couple at 12 Celsius. 12 degrees Celsius, it is 54? My math is escaping me at the moment. It's more than 50 degrees. Your rain is falling through air that is more than 50 degrees, and then coming back to the ground through a very thin, cold layer. I gotta imagine that's a warm raindrop. It's not gonna freeze like that. This is important to remember. As far as shifting gears and talking about the warm layer energy, and this is where we get into the Bourgogne technique, however you want to pronounce that. My boss with French aspirations would call it the bourgeois. Becky knows. Again, you've got some where you have very small amounts of warm layer energy, but you also have some that we're up to 600 plus joules of energy. That is a huge amount of an actual measurement of energy within here. And so some of these are pretty impressive. Now let's compare the two. So now we're getting crazy a little bit. On the y-axis, we've got warm layer energy in joules per kilogram. On the x-axis, we've got the warm layer temperature. The main takeaway from this is really just kind of a cool way to visualize how much our scenarios vary at times. Let's say you have a warm layer max temperature of 6 degrees Celsius. The warm layer energy within those cases has ranged from roughly 130 all the way to about 330 joules per kilogram. That's a pretty significant variation. It depends on how deep that warm layer is, and not just how warm it is, but how deep. And that raindrop is falling through that entire layer one way or another. So you get into things like residence time. Everything about warm layer energy should work better than just the max temperature. And so we're going to see that as we go. Now we get one layer deeper. I want to point out the labels here. On the left, we've got cooler drops. The actual axis is the net warm and cold layer energy. So you're taking that warm layer, you are subtracting out the cold layer. Hypothetically, you would have a liquid drop if your net is greater than 0. It's not quite that easy in the physical world. But as we go through here, I've also got the sizes and colors are dedicated to ice-liquid ratios. And this is one of the worst graphs I've ever made. What I want to point out here is that in the warmer net warmer drops right here, you have a lot more blue dots, which means basically warmer dots trend toward a lower ice-liquid ratio. This is one thing we can pull from here. And then I highlighted with the yellow oval, this is a scenario where the max temperature is actually similar to the min temperature in the cold layer in terms of raw temperature, but your net energy is greater than 200 joules. So you're saying these are the scenarios where you've got a really deep warm layer despite the temperatures being very similar. So these are also scenarios where you still have pretty low ice-liquid ratios. Well, you can't just look at points with this because this is noisy data. So let's get into a binned analysis of this, and let's just break it down for the operational side of things. Let's simplify it a little bit to where we can digest this into something. And so I break it down into scenarios with cold drops and light rainfall rates. If you take it back to the FRAM, the single greatest predictor of ice-liquid ratio is the rainfall rate. So if you have light rain, that's going to tend toward more efficient accumulation. So if you have cold drops and light rain, one would guess these are going to freeze well. And so you've got your box and whiskers is greater than 0.6 up to 1. Your mean and median are quite high. And then if you look at the scenario of warm drops and heavier rainfall rates, both of these elements are hypothetically going to lead to more runoff when the drop reaches whatever freezing surface it's going to hit. And you can see that here too. So again, you've got your mean and median are, oh gosh, about 0.1 to 0.15 lower ice-liquid ratio for these scenarios with warm drops. And I'm characterizing warm drops by the net energy. So net energy greater than 300 joules per kilogram, and then the precipitation rate as well. The question is, how much of this is actually important and when is it important? So we go a little farther. Let's look at warm drops with a cold surface temperature versus warm drops with a warm surface temperature. So surface wet bulb greater than 0.5 degrees Celsius. Warm drops in both scenarios. Your runoff is just going to be more efficient when you've got a warm surface. So what we're seeing here is surface conditions do matter, as we've shown with the FRAM, but independent of drop temperature, your surface temperatures are still very important. It makes sense, I guess, if I say it out loud like that now. Maybe it wasn't worth a slide, but we'll go on. Let's hit the net warm and cold layer energy and compare it to ice-liquid ratio. And so you got all these points, and the graph again is complex, but it's shifted a little bit. You still have cooler drops on the left, warmer drops on the right. You have hourly precipitation rate in your color. So the warmer colored circles, the bigger circles, that's heavier rain, heavier rainfall. And then along the axis, you've got your net warm and cold layer energy and ice-liquid ratio. So way up here, very efficient icing. Way down here, it's almost all running off when it hits the surface. Sure, you throw a linear regression on and you can see that that fits with such a high correlation that no one would ever question it. But there is a trend, and the trend is downward, that with warmer drops you are trending towards lower ice-to-liquid ratios. The downside in that, and one thing that popped out to me in this chart, is as you get up here, your warmer drops also correlate to higher precipitation rates. Notice how many more of them are at least on the larger size, and this is slightly closer to orange and red. Higher precipitation rates, more runoff, lower ice-liquid ratio. So what's really coming first here, the chicken or the egg? That's something we just need to dig in deeper. And so we do. And we do another binned analysis here. And this line is obviously hand-drawn, but I promise it was a true analysis. The graphing software just wouldn't let me do multiple things on top because I am cheap and I use Microsoft Excel and freeware. So right here again, you've got cooler drops on the left, warmer drops on the right, and your ice-liquid ratio in the vertical. They are all very similar until you get to the really warm drops, and then you start to taper off. Sure, you can follow a trend across the way, especially in the mean values here, where as you're getting warmer drops, you're definitely trending down. But the one that stands out to me is right here, and that's where we're definitely getting towards the lower end, maybe a little bit more here, where you don't have the high ice-liquid ratios. Your bottom line is still pretty similar, but you don't have the high values. So this is kind of an interesting thing. We're starting to tease out a little bit of maybe useful data here. How do we use that to improve upon the existing FRAM? And that's the big question, right? How can we actually use it to improve our ice predictions? And it's not an easy question to answer. Oh, too far, this is the only one you get. What I did was I went and basically said for the same binned analysis, versus observations, when does the FRAM actually overpredict or underpredict? And so this is not forecast dependent, this is saying this was observed, the FRAM predicted X and Y occurred. So here you go, cooler drops on the left, warmer drops on the right. And you're going to notice that there is a near zero bias until you get to the very warmest drops. So what I'm seeing here is basically this analysis is not particularly useful until you get a really warm layer. When you get a net warm layer energy of greater than 350 joules per kilogram, that's when you can start to say with some element of confidence that FRAM is over-predicting the ice. Independent, I mean, if I've got a perfect forecast for wet bulb, wind speed, and precip rate, FRAM is going to overpredict the ice because we're going to have more runoff because the drops are exceptionally warm in that scenario. So hopefully that makes sense. That is the one thing I've been able to tease out of it so far, and it hasn't been applied to the actual model yet because frankly I think we've got data issues. But if I was going to conclude one thing, I think it's right there. And so, on that note, conclusions. The first one is, some of these are just repeating, but the warmest drops in terms of net warm and cold layer energy, they're going to tend toward less efficient icing, lower ice-liquid ratios. This is not a rock-solid type of conclusion, but the tendency is there and it makes physical sense. You're going to get more runoff typically. The next one, in warm drop scenarios, so if you've got warm raindrops, a cooler surface wet bulb temperature results in greater icing efficiency. So independent of, what am I trying to say? It's what I mentioned wasn't worth a slide earlier. If you have a colder surface wet bulb temperature, it doesn't care if you've got warm drops or not. You're still going to freeze them. So that's that. Next one. Analyzing net energy parameters is more useful than using max T or max wet bulb temperature within that layer. And so that's why we're going to it in the forecast builder. This has been shown in the test bed to improve our forecasts, and it will continue to do so, I think. So that's a good finding, even independent of data quality. I think it's quite useful. And then finally, and I was happy to see this, admittedly, because I feel a lot of pressure every time anybody is issuing ice storm warnings. I really do. I'm watching y'all. Feel free to call me anytime. Seriously, anytime. Call the Omaha office as long as it's between 9 and 5 Central, Monday through Friday, and ask questions. No, I'm just kidding. Email too. I really am genuinely interested in helping with these forecast troubles because this is high-impact stuff. FRAM is really pretty successful even if you just use surface forecast elements. If you can make a perfect forecast for hourly precip rate, wet bulb temperature, wind, it's going to do really well. And that's because it's based in like some 2,000 observations now. It's a good number, pretty robust. We believe it can be improved, especially for those really warm drop scenarios. And again, this is something where if I was going to advise your forecasters anything, if you've got a really warm layer, then you can consider lowering it down, assuming the rest of your forecast is perfect. So that's where I'd go with that. Again, Chris is a huge part in this. He couldn't drive here from Grand Junction today, but just wanted to throw another shout out to him. And I think that is everything I've got. Nobody go anywhere. We're going to take a picture and talk some more. Thank
you. Are there any questions for Brian as we wrap up? Okay, thanks, Brian. Thank you. First of all, I just want to announce Tom